So hello everyone. This is supposed to be first session of third weekend, but I kind of forgot to start my recording at the beginning, so not much has been missed by the way. So I'll try to summarize what we covered so far and then kind of carry on from where we left off. So we're looking at linear regression as one of the class of algorithms, and the idea is to use some of the case studies that kind of made those algorithms popular uh, or relevant in the machine learning literature. And the problem we are trying to look at is the problem that Professor Ashenfelter uh, was trying to address of predicting the wine price in border wines in France uh, without tasting those wines. Till then the way it used to work was people would have wine auctions, and then there would be expert wine testers who would come take a sip of a wine, and based on their experience, would tell how much this wine is going to taste better. Let's say a few years from now, how much this wine is going to fetch money. And the price of border wines is such that it kind of varies from tens of euros to hundreds of thousands of euros. So it really depends on something else, so some X factor. And what Ashenfelter, who was the then economics professor at Princeton, decided to do was to not use wine testers, but try to use a quantitative approach to predict the price of wine by using some of the variables. And he constructed a data of previous 25 years of the for each of the wine, how old it was, what was the average season average growing season temperature in that time frame, how much was the winter rain, how much was the harvest rain, um, the age of the wine at that point in time, and decided to build a model which would predict the price of wine without tasting it in a quantitative way. And he decided to use linear regression. And we were kind of just building through this notion. And we stopped at a point where we said that it's not necessarily advisable to have all available features as your input variables to your linear regression. You can either do a single variable regression, which doesn't necessarily give you the best uh, R square or whatever metric that you are evaluating it on. You you obviously need to add more variables, but that also doesn't mean that you go and add all the available 100 variables. If you have so many in your data set, that can actually have a diminishing return. So how do you choose which are the best variables? And we were just kind of going through that example, and we stopped at this particular model where we said that if you build a model which uses uh, for example the previous model where we build the price, where we build a model to predict the price of wine using average growing season temperature, which is the AGST variable, plus harvest rain, plus winter rain, plus age, plus France population, which were all the variables available in this data set. Then you end up getting into a situation where your age tends to be least statistically significant. This is the p-value. This should typically be around 0.05 or so. Um, and it turns out that by that definition, you would pick AGST, harvest rain, and winter rain as the first three significant variables, and exclude both age and France population because both of them have a very low t statistic or a very high p-value. Now, this is where the domain knowledge kind of comes in. You are expected to believe that the price of wine would depend on the age of the wine, but not so much on the France population because they seem to be completely unrelated variables. But why is it that this model is giving an output where it suggests that the age is actually not a statistically significant variable? And it turns out that that's because of a phenomenon that's often seen in tabular data in machine learning called the problem of multicollinearity, where one or more independent variables that you use in modeling are highly correlated. Now, given our domain knowledge, we would want to keep age and kind of exclude France population, which is what we did in this next model that we built, which is model 4. So we kept age, and if you now look at the p-value of age, you suddenly see that it has become statistically significant once I took off the France population, which is an indicative. of the fact that age and France population may be highly correlated for no particular reason. In statistics, you will see lots of variables which are correlated to each other very strongly. They may have no causal relationship between them, but but they just tend to mess up your model. And this is an example of how you can mess up your model by including everything uh, without checking the multicollinearity conditions, and then you end up getting a model where you would have been tempted to remove age variable, but when you removed just the France population, you kind of saw that age suddenly became statistically significant again. Now, let's look at the notion of correlation. Again, we talked about this in the exploratory data analysis with the penguins data set last weekend. But if you just now look at the plot of winter rain versus price, this is what I'm showing here. Doesn't look like it has any linear relationship. The same plot which was on the right side in the right hand column in the when I was showing you the four plots above, doesn't look like it has any linear relationship at all. So you would expect a number, the coefficient of correlation, which is mathematically defined, to be close to zero. And indeed, there is a way by which you can compute it. And if you see that number turns out to be 0.14. Now, correlation is a number which can vary between -1 to +1. +1 essentially means that price is highly positively correlated to winter rain, for example. For example, if the coefficient of correlation for this data were 1 plus 1, then that would mean that if my winter rain increases by a unit factor, then even my price would also increase by unit factor. And then there is a coefficient of correlation which can be negative, which -1 means they are still perfectly correlated, but an increase in one leads to a decrease in the other. That's a negative correlation. And when your correlation is kind of close to zero, it kind of says that there is no linear relationship or no correlation between those two variables, which is what you can see here. Now, if you look at a plot of age and France population, which is what I was telling you were probably the reason why they were leading to multicollinearity. And now if I do a scatter plot of age and France population, even visually you can see that there is a linear relationship. The coefficient of correlation seems to be negative because increasing one decreases the other. It's a line with a downward slope. Of course, in Python and in many models in R, you can compute the correlation of every variable with every other variable. And that's what I'm showing here. For all the variables available in the data set, you would also notice, and this we spoke about when we were talking about correlation, when we were talking about the penguins data set last time, that the diagonal elements will all be one because they would be obviously expected to be totally correlated with themselves, right? And that's why the diagonal elements are one. And then you would want to look for those variables which may have uh, a high correlation minus towards -1 or +1, and try to avoid using all of them in your input model as your input independent variables in your model. Now you can see here, if you look at age in France population, their coefficient of correlation is -0.99, which clearly shows uh, the multicollinearity issue. So if I use both of these in my model, my model will suffer from a better predictive capability. So I should exclude one. Which I should exclude depends on your domain knowledge. Now let's build a last and final model where we just say that uh, for the just for completeness sake, let's exclude age as well. I mean, we said age and France population kind of complicated the multicollinearity issue. We decided to take off France population because we thought it was not likely that it would have an impact on the price of wine, but age of a wine could. But let's say what happens if we just exclude age as well and retain only those three variables. And then you can see that my R squared drops from 0.83 to 0.75. And that itself is an indication enough for me that clearly I need to include age if I have to improve the R square of my model. So your final model does seem to be the model 4, where we had those four variables, uh, AGST, harvest rain and winter rain, these three one plus age. right? And then let's look at how you kind of use this for a predictive ability. Uh, so what we do is I've given another data set which has only two rows really, uh, in which the price of the wine is also given and the other variables are also given. So what we would now do is we use that data of 25 years to build a model which we saved in this variable called model 4. Now we will use that model 4 and provide it all these variables, the independent variables values, and ask it to predict the price of wine and see whether it is kind of close to the actual price that is listed here. Typically, in machine learning, you wouldn't have this price column available in your test data set because that's what you're trying to predict. But here, just to kind of make the point, I'm giving the price also, and then we'll see what happens. So the way you do it is just call the predict function on that model and pass this data set, and it is predicting that the price of wine would be 6.77 and 6.68 compared to 6.95 and 6.49, which was the actual, which seems to be fairly close. Now, if you compute the SSE, uh, that and the SSE is now on the test data that we are computing. So what we are doing is taking the actual price, which is provided here, subtract it with the square of what we are predicting, that would be our error, and sum all the error terms, and I would get that SSE. That SSE is actually the lowest that I have so far. But this is of course on the test data. This is so you can't compare this with the training data that we used for the of those 25 years. You also can compute SST the same way we defined, and then you get an R square, which is 0.79. So R square seems fine. But when you are kind of summarizing your results, and this is a point I would like to spend a couple of minutes on before I move to the next one. You would also report the test R square along with the model R square, sometimes called the training data R square and the test data R square. Sometimes called this test R square is also called as the out of sample R square because it is out of the sample that you're used for training your data. So when you kind of summarize these results in terms of your R square or adjusted R square or whatever you use, you can actually then make a judgment and make a recommendation as a practitioner or as a modeler that we decided to figure out that these were the variables which led to multicollinearity, so we should exclude them. These were the variables which seemed to have to be most statistically significant, so we decided to include them. And this is a summary of the performance of models across all combinations, and hence we recommend that you go ahead with uh, uh, the fourth row, which is the model 4, which is AGST, harvest train, age, and winter rain, which gave us a 0.83 R square on the training data and 0.79 as we computed here on the test data, and say that that's probably the best model that you can come up with. Going back to the case study, uh, Parker, remember our Robert Parker, who was the expert wine tester, he said in 1986 is going to be good to sometimes exceptional year. Whereas Ashenfelter, with his model, predicted that 1986 is going to be a mediocre year. And he indeed said 1989 would be the wine of the century, and 1990 may even be better. So it turned out that eventually in wine auctions, 1989 wines sold for more than twice the price of 86, and 1990 sold actually for more than that. Later on, Ashenfelter also predicted that 2000 and 2003 would be great years, whereas Parker had predicted that 2000 is going to be the greatest vintage Balda has ever produced, which was never the case. So what's the conclusion? The conclusion is that a problem which was highly qualitative in nature till then, Ashenfelter had the courage to apply quantitative method to that problem. He had to curate the data set himself in the sense he and his team. They had to go and collect the data of all the 25 years, put it together in a form which was usable for modelable. Then they built the models. They argued about the mathematical and statistical uh, inconsistencies. Eventually, picked up the most articulate and statistically significant variables that gave the best performance, and came up with a model which predicted the price of wine without ever tasting it. So the biggest contribution of this approach and this case study was that I think the last bullet that I've written in conclusions, which is that it kind of applied a quantitative approach to a largely qualitative problem. So when you look at a problem, you may be tempted to believe that this is not solvable quantitatively, but you must understand that uh, what seems unnatural uh, or or impossible at the beginning kind of does seem to give you pretty good results. And linear regression wasn't new, as I told you. Till then, it's been 100 years old uh, by then, and yet it wasn't applied in the context in which Ashenfelter applied. And when you do that, it gives amazing results. Linear regression is highly one of the most highly used but highly underutilized model. Also, I think the judgment that a machine learning practitioner or a deep uh, or a data analyst uses or a data scientist uses uh, in terms of making assumptions and figuring out which variables are going to be a play, that is the harder part. But once you can get hold of that by picking in the domain knowledge and stuff like that, then I think linear regression is can still be the simplest but the most effective model that you can use even today. And tomorrow, my plan is to kind of show you some of the use cases where people have even kind of built companies, startups in healthcare, where they use as things as simple as linear regression. From here on in this notebook, I'm kind of showing you how to use this using scikit-learn. So I'm not going to spend time on this, and it kind of you will see that it kind of gives you the same numbers as 0.83 and 0.79. So this is just a way for those who are interested in development to kind of compare stats model versus scikit-learn and kind of start getting used to the notion of scikit-learn the way it is here. So that's so much on the linear regression. So the basic takeaways are know your domain, know your data set. And by know your data set, I mean know which variables are highly correlated. Don't use them necessarily. I mean, it's not necessary that multicollinearity will always give you a wrong result, a wrong prediction. There can be other factors, which is again something I'm going to talk tomorrow, which generally comes under the terms called dataset shifts, and that's a big topic uh, of research today. And I would love to talk about it for at least an hour or so, or at least half an hour or so, or 45 minutes, depending on time, on a dataset shift and why it is so critical. But know your dataset, that's more important. Uh, Multicollinearity will be an issue if you're doing linear or uh, multivariate regressions, and then proceed along. Now, what I've shown you here is a linear regression. You can also try to fit a nonlinear or a polynomial equation, and there are standard methods for that. The basic methodology still remains the same. You still you still progress the way I have kind of shown it here. That logically takes me to the next topic, which is talked about in the order of complexity, is the logistic regression. Now, the f- the first misconception a lot of people have is this is about regression. It is regression, yes, but it is not a regression in the sense of the term that we use in linear regression. Logistic regression is actually a classification algorithm more than a regression algorithm, but it uses a line to fit for classification. Hence, the term regression appears. So don't get carried away by the fact that it's saying logistic regression. It's actually a classification algorithm, and that brings me to the first natural point of discussion, which is the difference between what is regression and classification. Now, in the last example, we were trying to predict the price of wine, which is a number. It can take any value, right? I mean, we talked about it taking values from tens of euros to hundreds and thousands of euros. We converted that into a logarithm, fine, but it's still a number. At the end of the day, you're trying to predict a number. So if you are For example, building a model to, let's say, predict heart rate, for example, or systolic blood pressure or diastolic blood pressure, or glucose levels, or whatever from the data, which is a number, or the height of a person, or the weight of a person, for example. And if you're trying to build a model which is going to give you as an output some number, some continuous number, it can take any value, you always end up using regression models. Linear, single variate, or univariate, or multivariate, or polynomial, that's a choice that you take. There are tens of other regression algorithms which we don't have time to go into, but you could look up them in scikit-learn, for example. It implements all of those algorithms, but that's not the point. The point is you are still trying to your outcome variable is still a number. When your outcome variable is not a number but a category, that is when we call it a classification algorithm. In this sense, uh, instead of, say, the same problem in wine which we were talking about predicting price, let's say if I further binarize that variable of price, and let's say I create a new feature and say costly or cheaper. Now, if I translate the price of wine into only these two categories, that the wine is costly or cheaper, by using some idea, some thresholding, whatever, but I decide to call one particular wine costly, another cheaper, and so on, then I'm only predicting costly or cheaper. I'm not predicting the actual price. That's the time when we are actually predicting a category of a variable, and that's when classification algorithms are useful. And majority of algorithms that you would see in healthcare, except for the physiological time series data that you use, which is the one I explained, there you will use regression, but majority of them you would end up using classification algorithms. Logistic regression is one of the simplest classification algorithms, which I'll explain now. And then time permits, we'll talk about decision trees and the other algorithms. Else we'll carry kind of uh, that might overshoot into early part of tomorrow's session. Now here is a diagram which I actually have been using for quite a few years now. Uh, but since March 2020 and the pandemic times hasn't been more relevant than ever before. Is the quality of healthcare that we provide able to, is it able to help our patients survive, or does it sink them? Now, here is a problem I'm going to show you with another case study. Like we talked about wine in the case of linear regression. I'm going to talk another case study for while talking about logistic regression. And we are going to basically predict whether the quality of healthcare provided is good or poor. So it's a category. We are not necessarily trying to predict a number here, but we are simply going to say whether the quality is good or poor. And because it's predicting one of the two values, it becomes a classification algorithm. And the idea is this: I'm going to use an example from healthcare here, just to kind of not feel that healthcare is being totally excluded. That is one reason. And the second reason, important reason why I've chosen this example is because it also brings you uh, insights into how do you kind of curate your data sets. It is it is an assumption, a myth, that people believe that data scientists' job only starts after they are provided with a data set. And I've said it often before. The biggest job of a data scientist or a machine learning practitioner is to actually put together a data set on which you can build a model. I remember making this point in the first lecture on 3rd of July when I said that like almost 80-90% of the task is putting together a data, and then modeling is really is the glamorous part of the work, but not the one that takes so much time. Putting together a data set takes a lot of time. Now, whether it is 90%, 80%, 60%, that's a cliche term. But the whole point that I'm trying to make is there is a significant amount of time a data scientist or a uh, practitioner in machine learning does spend and should spend on just putting together a proper data set on which you can then build a model. And this example that I've picked up here is just a way of giving you an insight into how it can actually be very difficult. And when you don't know anything about the problem that you're trying to solve, and yet you need a data set, how do you go about doing that? So the problem is this: the problem is of trying to model the experts, which are the physicians in this case, because we're talking about the healthcare and the quality of care provided. Now, a lot of critical decisions are made by people with expert knowledge, and that's why we kind of go to well-known doctors and well-known hospitals, and so. But healthcare quality assessment is difficult because, but it is important. Now, why is it important? Because good quality care actually educates patients and controls costs. Otherwise, you would be just kind of going around conducting hundreds and thousands of tests, and you wouldn't know whether you are doing good or not. But this assessment of quality is also required for medical interventions, for example. But the problem is there is no single set of guidelines for defining what is a quality of healthcare. And unfortunately, even more unfortunately, is the fact that the health professionals who are the experts in the quality of care assessments are not that many. Now, they are humans, so they are limited by time and memory. Uh, they are far and few. Now, how do you kind of try to build a model or try to build a system quantitatively where you can capture this knowledge in some form, in some abstract quantitative form, and then try and replicate it to a population of millions of patients around the country, around the world, wherever. So replicating expert assessment is what is the desirable characteristic of this exercise. So can we develop such tools? Can we learn from the expert human judgment? Can we build a model, interpret results, adjust the model based on what we learn, and then make predictions on a larger population? And then say that based on these parameters that we saw in another population, can we say that the quality of care that they're getting is good or poor? That's the larger goal. But you are dealing with a problem where you are dealing with a very few human experts who are going to give you that insight for a very few patients. So this was a data which was curated around the time uh, when the medical claims data. So now, as I told you again in the first session, lots of these data sets come from the Boston area because of proximity of the academic institutes to the medical hospitals, and everything in healthcare in US is driven by insurance. So a lot of data is available with insurance claims. So the idea was at the time, can we take the data from medical claims and kind of convert that into some kind of a data set from which you can then build a model and then take that model and apply it to other populations of patients where and to predict their individual outcomes of whether they are being provided a good healthcare or a poor healthcare. Now, here is a problem. The reason I said 60-70% of problem you time you spend just curating the data, here is the problem. Typically, your medical claims data has both medical claims and pharmacy claims. Now, medical claims are diagnosis, procedures, doctors, visits, cost captured in some form. And now each of them are not necessarily standardized in any format. And your pharmacy claims are what drugs were prescribed, how much quantity, which was the doctor who prescribed it, what was the medication cost, and those things. Fortunately, in US, this data is electronically available. I'm not too sure whether we have fully electronically data available in India. Fortunately, it is a bit more standardized in the US. Uh, we may have just blindly followed their protocols, so then it may be a bit standardized here as well. But clearly, it is not 100% accurate. Underreporting is a common thing because there are reasons why underreporting happens in medical claims. I don't want to get into those details, but that happens. So given the kind of dynamics that you have like this, how do you kind of create the data set? So what was done was they took a sample of the medical claims data from a large healthcare insurance database company and selected randomly 131 diabetes patients whose ages ranged from 35 to 55, and their costs of uh, treatment or whatever, uh, cost of healthcare varied between 10,000 to 20,000 US dollars. And this data was collected for patients between September 1st, 2003, over a period of 2 years. Now, expert physicians reviewed this data. These are 131 patients, so human experts can handle this data. But can you take this data from 131 patients, build some model, and take it to millions of patients? That's the task we are looking at. But it was possible to at least give this 131 patients data to the expert physicians, and what happens is in a lot of medical claims which they reviewed, the notes are very descriptive in nature. They are written in English. They may or may not be full sentences. But then when you are trying to put together a data set, your job is to kind of convert this English descriptive language into some kind of key keywords. For example, there may be words like ongoing use of narcotics. Maybe it would say the patient was only on Avendia, which is not a great first choice drug. It may also say the patient had regular visits, mammogram, and immunizations, uh, was given home testing supplies, for example. Now, what the expert was requested to do was to kind of go through an assessment where they would say uh, from looking at these data, they would basically say on a 2-point scale whether the quality that was provided was poor or good. But the problem is they were not creating this data set. They were assessing the reviews, the claims review. They were reviewing the medical claims. So even the experts would end up writing like, I would say care was poor. This was a purely treated diabetes patient. No eye care was taken, but overall I would say high quality. Now, when you are converting this into a data set, you can't simply pick up the word care, and because here it says care was poor, sometimes it may say care was not good, and you can't just look for the keyword good and try to say that the care was good because it is actually saying not good. So you have to not just look at one particular keyword, but the overall semantics of the English sentence to even create a data set which is meaningful. And that's a challenge, and that's the reason why I'm kind of showing you this data set, because it is very difficult by going from English descriptive notes uh, through the process of curating your data set. But at the end, the idea was to extract dependent variables and independent variables. For example, from this sentence like ongoing use of narcotics, you may just pick up the keyword as narcotics and call that as a variable. Maybe on drugs, you'd call that one variable. Home testing supply, regular visits, mammogram, each of them you may want to call as an independent variable or a feature. And then from the notes that the expert physician wrote, you would also convert that into uh, a variable, a binary variable, which takes a value of 1 or 0. Now, the variable that was called was poor care. So if that value is 1, then it actually means low quality care. If poor care is 0, that means the patient actually got good care. So this is a categorical variable, right? Now, this is where the notion of logistic regression kind of comes in, because you're now trying to uh, predict a class and not an actual value. Now, I'll set this up and show you the data set. But before that, uh, I just want to set up the mathematical construct, at least at a very high level. So we have this variable, let's say poor care, let's call it y. And you want to predict the probability that that value is 1. Like that's what you want. then you would also be able to subsequently compute the probability of that variable taking value 0, because there are only two possibilities. So 1 minus the probability of y equal to 1 is the probability that y equal to 0. And then you define a bunch of independent variables which are extracted from these descriptive notes that are written. Often an expression takes this form called 1 by 1 plus e to the power minus x. This might look a fairly complex function, but just look at this as just 1 by 1 plus e to the power minus x as a form. And I will just try to show you plotted it here using the code. All I'm trying to plot is this function 1 by 1 plus e to the power minus x, where my x actually varies from minus 10 to 10. So my x is actually going from minus 10 to 10. I've selected 20 data points in that range, and I'm trying to plot the value of this function. Now this function is very unique. As you can see that it has a shape of an S curve, which is why sometimes this is called as a sigmoid function, the same sigmoid that you would have heard in deep learning and others, which we'll cover next weekend. It also kind of returns values which are always between 0 and 1. And that's the notion of probability that we were trying to build in. So any number, any function that gives me values between 0 and 1, I can kind of interpret that as the probability of a particular event. And and the sigmoid function, which is 1 by 1 plus e to the power minus x form, allows me to kind of do that, because as my x values go closer towards infinity, minus infinity, my value of the function goes close to 0. As my value of x goes close to plus infinity, my values of this function kind of get close to 1. It's asymptotic on both sides, never actually becomes 0 and 1, but takes this shape of S curve or the sigmoid curve. That's why this function is sometimes called as the logistic regression function, sometimes it's called as the sigmoid function. It takes the form 1 by 1 plus e to the power minus x. And what am I showing here as x is the same form that I showed you in the earlier notebook when we were talking about linear regression, and the multivariate case is the same form, beta naught plus beta 1 x1 plus and so on up to beta k xk. So this is the line that I'm talking about, and this is the form that this function takes. It will be very obvious in just a couple of minutes as to why we are putting this regression function in this form. The notion of probability has relation to odds, and this is very something I learned the hard way, and as some of you may know it who have been in the healthcare side, but I kind of uh, learned that that people in the healthcare domain, medical doctors, are generally averse to maths, and generally they don't like to do division. I mean, at least that's what I've heard from some of the people who have been in this field. They don't like to look at a probability of an event as some number which is like 0.637 or something. To get that number is that number itself is scary enough, and to get to that number you have to do some additions and subtractions and divisions, worst case, and that's not something which is likable by the medical fraternity. So what they always tend to use is not use probability, but use this notion of odds. And some of you who follow sports uh, would have heard this term that somebody is an odds-on favorite to win a particular tournament or something. Odds is related mathematically very precisely to the probability using this formula. So for example, if my y variable is poor care equal to 1, then my odds are basically saying probability of y equal to 1 divided by probability of y equal to 0. Now let's say my probability of poor care was 0.25. So that means my probability of uh, good care was 0.75. But my odds are written as 0.25 divided by 0.75 or 1 by 3. And I would say I wouldn't write that number as 0.33 because healthcare people don't like fractions. So I would just say 1 is to 3 odds or 3 is to 1 odds if it's the reverse way. So if my odds are greater than 1, then that means my y equal to 1 event is more likely. Like for example, 3 is to 1 means this is 3 times this value. That means this event is going to be more likely. But if odds are less than 1 or equivalently to say it as 1 is to 3, then this event is going to be more likely, which is the other event of getting good care. Using this notion of odds and this expression that you saw here, 1 by 1 plus e to the power minus x, let's say we define a logit as in the following manner. So e to the power beta naught or whatever that you saw, let's say call that as odds. Then if you take the logarithm of odds, you get beta naught plus beta 1 x1 and all the way up to this, which is essentially the right hand side is essentially the linear multivariate regression case that we did in the last notebook. And whatever we get would be logarithm of odds. From logarithm of odds, I would be able to get the probabilities and back to uh, what I really wanted the problem as. But I just typecast that problem from a probability computation problem into a odds problem. And this is what is called as a logit because it looks like a linear regression. Now, let me show you the data set and then I'll explain this concept of where the line is coming here and why it's called regression and why it is yet a classification problem. But if you just go ahead and run some of these cells, I've already done that here just to save time. And if you look at the first few rows of my data set, it has obviously some patient ID, then inpatient, uh, how many days was the patient in the hospital, how many times the ER visits were done, how many office visits were done, whether narcotics was applied, how many days since the last ER visit, was there pain, how many times the patient has visited, who is the provider, how many times it comes, medical claims, how many times were filed, s- many others, right? And eventually the last variable is poor care, which can either take a value 0 or 1. Now, remember, these words are coming uh, from natural language processing of the descriptive notes that the doctors and the nurses have written. So this was not the data set that was evidently available from day one. This was a data set that had to be curated and prepared from a very descriptive English text. And from there, count these words, how many times narcotics words appears, and let's just count that and put it together. Now, the veracity of this, remember I talked about the 4 V's of healthcare data, uh, variety, volume, velocity, and veracity. Veracity is in your hands. If you are the one in charge of putting together this data set, then you should be convinced that every value that appears here is actually corresponding correctly and reflecting correctly from the descriptive notes that were written earlier. Now, that task of moving from descriptive notes all the way up into getting a tabular data can actually take a lot more time than it probably took for putting together the Wines dataset, which is why in this case it may be cliched, but you might still take 85 to 90% of the time of the project just putting this data set together. So never assume the data set is available. Always believe that from things which seem very abstract, like handwritten notes or things written on a piece of paper, can be converted into a proper tabular data set. That task is on you as a data scientist or a machine learning practitioner. And what these people did was they just took this data set of 131 patients, ran it through physicians who were the experts, who said, based on whatever they saw or read in the claims data, they said whether the patient got a good quality care or a poor quality care. But that was still English descriptive text. From all that description was this data set converted into some kind of a tabular data, which has numbers in it. Okay. So just the point that having a data set available is an assumption. It's really your task to do it. And now let me come back to the definition of odds and the data. Now let me show you office visits and narcotics as two variables because that's what I'm plotting. So I'm showing you a scatter plot from this data set where I'm just taking the two columns, office visit on x-axis and narcotics on y-axis, and you will see that they're color coded. They're color coded based on what quality of care was offered to them. So poor care are red, good care ones are green. That's the code that don't bother about the code part, but look at this scatter plot as something which is now not predicting the price of wine as we were doing as a number in the earlier case, but now trying to predict a class of uh, the healthcare provided as poor or good, and you can only color code it uh, as two colors because there are only two classes, and here you see a distribution of this. Now let me pose the problem. Just as I was trying to show you whether a red line was a great line or a blue line was a great line or a green line was a better line in the linear regression case. Let's proceed with this problem in an intuitive way. Let me say I still want to draw a line, which is where the term regression comes in logistic regression, because I still want to fit a line to the data. But I don't want to fit the line to the data in such a way as to ensure that majority of data points lie either on the line or close to that line, which was the task when we were doing it in linear regression. But here I'm using the line that I'm fitting as almost line as something like a line of my decision boundary, and say that any point which is below this line, for example, this blue line, will be classified as the patients who got good care, and anyone above this line uh, got a poor care, because I just see that majority of points above this line are red and majority of points below this line are green. So I want to build a line which will allow me to fit it to the data that I have and yet use it for classification task and not predicting the price of wine as we did in the linear regression case. That's why the terminology can get confusing. Here we are talking of a logistic regression as a task of fitting a line, but the idea is to fit a line to classify the data, not to ensure that data points lie on that line. So anything below is green, anything above is red. Now, we talked about the baseline model as the worst case model in linear regression as one where we just took the mean value of all the price and said that red line, which was the horizontal line, predicted the same price of wine irrespective of what my input variable was, taking the value, AGST in that case. Here, how would you do that? Here, you're not predicting any price. So you're not working with numbers. It doesn't make sense to take an average of numbers which are either 0 or 1, because that doesn't give much more insight, because we are talking of classes and not numbers here. So the equivalent notion of a baseline model in classification tasks is you just count how many times a particular variable uh, appears. Now we have this data set of 131 diabetic patients, and if I count how many times it is 0 and how many times it is 1, it turns out that good care was offered to 98 patients, poor care was offered only to 33 patients. And then I define my baseline model in classification task as the one where my where I choose that as the prediction which is most frequent. Now between 98 and 33, 98 is more frequent. So I say I build a baseline model which is not taking any value from the input variables. I'm not taking any value of narcotics versus office visits, but I'm saying I'm building a model which always predicts 0 as good care. Which always predicts 0 as a poor care value, which always corresponds to good care. Why is that intuitive? Because of this notion of majority that I talked about. So I have not used any dependence on the independent variable. I'm always predicting 0 as the poor care variable. And if you look at it, 98 times out of 131 cases, it will be right. That prediction would be right. Only in 33 times, in 33 cases, it will be wrong. That stated otherwise is the baseline accuracy of my model. So my baseline accuracy is 98 divided by 131, which is 75%. So if now I'm going to build a model which is going to have its own accuracy, I would ensure that that model at least has an accuracy of 75 or above. Because what's the use of building a model if it's not even going to give me the baseline accuracy? And my baseline accuracy is just that model which predicts the most frequently occurring outcome as uh, as the baseline model. In this case, it is a poor care value taking zero. So 75% of the time, my worst case model predicts correctly anyway. So I should build a model which at least does better than 75. And that's where a baseline model is useful. We had a red line whose SSE when we were talking about linear regression was 10.75 or something. And then we wanted to build a model whose SSE would be better than that. Here, my accuracy of a baseline model is 75. And I'm talking of accuracy because I didn't talk of accuracy in the case of linear model because there we were predicting a number and we were using other methods of evaluation such as R square, etc., to qualify whether a model was better or worse than the baseline model. Here I have to either say my poor care is 0 or 1, right? That's the only thing I can predict. So if I'm predicting my poor care is 0 and the actual poor care was 0, then my accuracy, then my model is correct. If a poor care was 0 but I'm predicting poor care as 1, then my model is not correct for that particular instance. So I can talk of accuracy. And the way we talk of accuracy of a baseline model is by just talking of it as the most frequent uh, outcome. So now we need to kind of define uh, the notion of a model, whatever way we build it, it must at least be able to predict the accuracy which is better than 75%, which is my worst case model. Now there is a notion which I'll explain in this diagram a little more and then we'll stop. I know we are closer to the end of today's session, but these are terminologies which are important to talk about whenever we talk about classification algorithms. So I'm using it in the context of logistic regression to talk. So this session might go longer tomorrow, but uh, trust me, these are the terms that you'll keep hearing all the time whenever you come across any machine learning work. So it's better to understand those things. When we were talking about the linear regression, I showed you the 25 years data, then we built a model on that data, and then we loaded another data of 2 data points, which we called as the test data set. Now imagine you are dealing with this kind of a data set where you have to curate the data set, this medical claims data, which is a very painful process of going from handwritten notes or descriptive English notes, even if they are in electronic form, to to capturing them in a data set form, in a tabular data form. Who is now going to give you the test data set separately? As it is, it was tough enough to create 131 data set point. It is too much to dream that somebody will come from the heavens and give you separate data set which you can then use as a test data set. So what is often done is this trickery in machine learning. You have this, so the way to look at this this diagram is from left to right. So this cylinder is what I'm showing you as a data set. Let's say this is the 131 diabetic patients data that we have. And then what we do is we split this data itself into two parts. One part we use to train our model on, and one part we use to test our model on, which we kind of hold out or set it aside, which is called as the test data. And whatever training we do is done only on this training data set alone. At the time of training the data or training the model, we are not aware of existence of this test data. Once we are convinced that we have built a model like were doing in the linear regression case when we were experimenting with 4 or 5 different models, let's say we do that, and now we believe that we have come up with the best possible model that captures the intricacies, the training data. Then we take that model and run it past our test data and determine the accuracy. That's when we test the model. That way, we can say quantitatively that my model is like 80% accurate, 85% accurate, 90% accurate. These terms you would have heard 100 times. What does it mean? It basically means that if I set aside 10 data points in my test data, if my model is 80% accurate, it essentially means that whatever my model I trained on my test data is able to predict correctly in 8 out of 10 cases in my test data. If my accuracy is 90%, it means I'm able to predict 9 out of 10 times correctly. Now, how big your test data set is a function of how big your original data set is. So it's a call again that you as a practitioner take depending on looking at the test size, looking at your data set size as to how big your training data set is going to be and how big your testing data set is going to be. And first of all, how do you even may find these two things? And that's the point where we'll start off tomorrow and talk a fair bit of metrics and evaluation things in the context of logistic regression, but which will be something which we will use also for decision trees and random forest, and for that matter, any other machine learning algorithm. So we'll spend some time on that, which is prime, and I'm talking about confusion matrix, sensitivity of model, specificity of model, precision, recall, F1 score. These are the things that you would have heard. And what is an ROC or a or receiver operating characteristic, what is the area under the curve. These are the terms, if you come across any ML literature, would be reported as part of of the results section in any paper. And these are the things which will kind of explain in the context of this data set. That's the task we will do tomorrow. So we'll break for now. Thanks everyone and see you tomorrow at 3 o'clock. Thank you again.